Yes, sir.
Yes, sir.
Okay, so before we move further down the lane, we are going to do some recap on what we have learned before the semester leave, okay, before the festive leave. Okay, so in week 8, we have discussed a bit about angular kinetics and we stop at angular momentum, right? I think these are the example that been given to you. Okay, so angular momentum is actually the amount of movement you have during angular motion. Sama lah macam linear momentum. Okay, when we talk about momentum, we can define it as the amount of movement. So in linear, the amount of movement is actually straight line movement. Okay, amount of movement, linear momentum is something like this. How much a thing move? What is the amount of movement? Amount of movement in linear. This is known as momentum. Berapa banyak dia bergerak. And always when we talk about momentum, it being caused by impulse. Okay, ataupun external force. Impulse is actually a form of external force, means we inflicted force to the object. Okay, the point of impact, we are going to transfer impulse, and when you transfer an impulse to an object, it will cause the object to move. If the object moves straight, this is known as linear momentum. Okay, how much movement? Okay, where we can have it as momentum equals to mv, mass of the object times with the velocity. So the higher the velocity, the more momentum the object will have. Ini linear. So in angular case, it is actually the same thing, but instead of moving in a straight line or a curve, in angular kinetics, angular momentum is the thing, is when the object rotates. So when the object rotates. So here we have mass, we have velocity. But in angular momentum, it is actually dia punya moment of inertia. And then the omega. So how fast the rotation occurs is the velocity in terms of angular, and the weight or the mass of the rotating object is the moment of inertia, ataupun dia punya berat. Okay, and as we have mentioned before, when the case is angular cases, the larger the radius, the heavier it will be. Okay, the larger the radius, the heavier the object will be. Means that the rotational velocity is going to be slower. But if the radius is shorter, okay, radius 2, okay, radius 1 lagi besar pada radius 2. If the radius is shorter, you are going to have less mass towards the system, which means that the rotation is going to be um, speedier, is going to be faster. To case angular momentum lah. So when we this is um, the principle, okay, same as linear momentum, where we have principle of momentum conservation. Momentum before collision is going to be equal with momentum after collision, but in angular momentum, it is actually momentum for every single phases of action. Okay, in any single phase, in any action, if we divide the action into phases, every single phases will have similar angular momentum. The difference is just towards whether you are going to have more radius of rotation compared to less radius of rotation, which resulting, if you have more radius of rotation, you are going to increase the moment of inertia, the mass of the system, which resulting, if the mass is high, the velocity will be low. When you in a position where the moment of inertia is less, means that kamu dalam proses tucking or whatsoever, in this process the mass is less, resulting the velocity or the omega of the system will be higher in order to balance things up. So if you have a quite a balanced angular momentum throughout the phases, the action itself is going to be a fluent action. Okay. However, if during the process you end up with quite a staggering amount of angular momentum difference between each phases, it will result towards uh, uneven action ataupun you are not going to have the intended action. You tend to have a pike, but at the end of the day, it is actually a splash. Dia macam itulah. Itu untuk angular momentum. Okay, so these are the principle of angular momentum conservation. Means that every single phase, the angular momentum amount is going to be equal. The difference is just towards the amount of moment of inertia and also the amount of angular velocity. That is going to change in order to balance things up. Okay, so these are some of the definition for angular momentum. When angular momentum is conserved, there is a trade-off between moment of inertia, the mass, okay, the angular mass, and angular velocity, the omega. All right. So we move on. As we have known, as what I have jotted down here, in linear kinetics, when we try to have momentum, we need to have impulse. Okay, I equals to F T, M equals to mv. So we have I equals to m. Same as here. Okay, same as here. So we have angular impulse, the product of torque and the time interval over which the torque acts. Okay, so torque is angular impulse. Alright, torque is angular impulse, or to be exact, angular impulse can be defined as the change of angular momentum. Okay, the change of angular momentum. However, if we take a look at the definition for linear, uh, the correlation between impulse and momentum linearly, Ft equals to mv, this correlation is also true to angular impulse. Jadi kita ada angular impulse. This is the angular impulse. We have equals to change of angular momentum, meaning it going to be mk square omega. Okay, is it? Kita balik minus mk square omega. This one is the second one. This one is the first one. The change of. Okay, it is the change of. Right. Other than that, let's put this in form of angular. Okay, let's put that in form of angular. So we know in angular, force is torque. Okay, saya ada bagi kat belakang ni sebenarnya. Ni. Force is torque. Okay, so angular impulse is torque and time. Sama. Okay, so we have Ft linearly. In angular, it's going to be F ni torque. Means it is Fd. So kita adalah Fd T, angular impulse. And momentum, okay, momentum in linear is m is moment of inertia. It will be mk square ataupun I, and then v will be omega. So in angular case, we also can see, okay, sometime if the information being given is the information of momentum, this is how you want to find torque, change of momentum. But if you have all the information other than that, you can also see angular impulse is Fd T, impulse. Okay, and it also equals to mk square omega. So angular impulse torque equals to angular momentum. These are equal, sama. Okay, jadi ni I equals to M. So either one you can use. Ni linearly, ini angularly. Okay, ini yang pertama dulu. The derivation of it. Okay. Alright. So angular impulse is also change of torque. Okay. Angular impulse is also FDT. Okay. So apa sebenarnya angular impulse? Alright. In linear, apa itu impulse in linear? We recall it back. Okay. Impulse is the amount of force given towards a period of time. Means if we have a ball, we kick the ball. How much force delivered to the ball and how much contact time between the leg and the ball. Okay, macam saya cakap sebelum ni. We have a ball, we kick the ball. During that process, you are going to have a contact process. You are going to have a drive process and you are going to have a separation. Okay, macam ni. Bola, kaki, contact, first phase. And it goes to the second one where the ball is in contact and drive forward. And then it will goes to the third phase where the ball start leaving the leg, which is the separation. Contact, drive, separation. Where in linear case, impulse is the amount of force being transferred to the ball, which will cause the ball to move forward. Itu impulse. Newton's second law. Okay, itu linear impulse. So, in term of angular, katalah kita ambil bola lah ni kan. In term of angular, it is actually when we give an amount of force to the system which will cause the system to rotate. Ini angular impulse. Okay, that is angular impulse. So we have F, we have D, we have T. F, clear, amount of force being given. Okay. T, the time contact between force and ball. Means drive phase. Okay. F tadi, dia punya contact phase. Okay. D ni, apa itu D? Okay, we recall back what we have learned beforehand. D is distance. But in term to make a thing rotate, the distance is actually dia punya radius. Okay, radius apa? Alright. Let's say we have an object. Okay. Now, if I give a force like this, what is going to happen to this box? Apa jadi dekat kotak ni kalau kita bagi force in this direction, in the middle of it? Jadi apa? What is going to the box? Ini case linear. Okay, apa jadi? What is going to happen to this box? Come on, guys.
Move forward, sir.
Move forward. Now, what if I give force to this box like this? What is going to happen to the box? Kita bagi dia dari sisi. Kita tak bagi tegak-tegak. It will cause the box to
Rotate.
rotate. So radius dia mana? Mana dia punya paksi? We need to know that first. Okay, let's imagine the paksi in the middle as always. So we know that this box is going to rotate like this. Setuju? If we give force here. Setuju tak? It will rotate like this.
Yes, sir.
Memusing lah. It will memusing-musing. Okay. So the D here is actually you need to have, again, ni benda yang kita dah bincang. Draw the line of force, and then you need to draw a line parallel to the force, intersecting the axis of rotation. So kalau force macam ini, kita kena draw satu line parallel, okay, sejajar dengan force, intersecting with the axis. Okay, so the distance between the line of force and the axis, the line that intersect with the axis, this is dia punya D ataupun radius of rotation. Okay, katalah kita ada satu lagi kotak, but now it is not sini. Okay, it is not sini. It is actually begini. Okay, we give this kind of force. Jadi, di mana radius dia? First, you need to have much more elongated line of force, straight line. And then, draw a line parallel to the force line which intersect with the axis of rotation. And then, a straight line from the force to the axis of rotation between those two lines. Okay, perpendicular to these two lines. Apa maksud perpendicular? You are going to have 90 degree. These are the distance or the radius. Ini cara untuk kita tentukan distance for angular impulse ataupun distance for torque. Okay, because not all torque, not all force in a torque being given in a straight line towards the axis of rotation. Contoh macam ni. Tangan. Okay, ni contoh biasa. Bicep. Beban. Bicep pull the force upwards. Beban pulls the force, the hand downwards. Axis of rotation dekat sini. Axis. So dekat mana dia punya radius? Okay, the radius will be from the axis to the force. Why? Okay, because the force move upwards in this line. So we need to have another line parallel to the line of force intersecting with the axis. And then straight line connecting those two. Okay, daripada axis tu ke force. And this line need to be perpendicular. So these are dia punya radius ataupun that are dia punya distance. Nama lain dia apa? Force arm. Tu sebenarnya. Okay. So all of this line is actually force arm. Jadi kalau kamu dapat tengok tiga nama ni, janganlah terperanjat. Kejap nama dia radius, kejap nama dia distance, kejap nama dia force arm. This all three is the line perpendicular from the force to the axis. And this actually the thing that show you the D part, the distance part, which make up torque. Ni. Okay, torque. And when you apply time to the torque, you get angular impulse. Okay, angular impulse. Jadi angular impulse ni kita letak macam ni, TT. Torque equals to change of H ataupun equals to FDT. These are angular torques. And when we give angular torques to an object, let's say human, okay, we give angular torques kepada dia ni, apa yang akan terjadi? It will cause rotation. Jump and rotate, that cause torques. Okay, that is the product of torque. Ataupun kita ada kaki. Okay, we need to kick the ball. We need to kick the ball. So how much force needed in this system? That is torque. Okay, that is torque. How much force being delivered externally? This is impulse, because this one is linear. And how we get the linear one is by rotating joint. Is by rotating body parts. So all those rotating body parts the amount of force being described in terms of torque. Okay, saya bagi satu contoh. Alright, so we have, kita ambil kaki ya, we have leg, and this leg is swing. Maksudnya dia tengah berayun. Okay, when we talk about swinging leg, we know that the swing originate here at the head of the femur. Okay, at the head of the femur, those joint, okay, those ball and socket joint rotating, causing the leg to swing. Okay, macam mana pula kaki kita boleh swing, boleh rotate tadi? How can the femur joint, okay, how can the ball and socket at your femur rotate? It caused by contraction of several muscles. So we have quadricep and hamstring attached to both the upper and lower part of your thigh, and the contraction and relaxation of those muscles, the agonist and antagonist function of those muscles, causing the bone to swing. Okay, and it swung at the joint of pelvic and femur. Okay, at the ball and socket. Okay, now my question. Now this leg swing at 8 radian per second. So the omega for this leg is 8 radian per second. The question is, how can we make the leg stop? Okay, and let's say the moment of inertia, the moment of inertia of this swinging leg is 0.7 kgm square. Okay, katalah kita tengah menumbuk, okay, kita tumbuk. Alright, now please do an action of punching. When you try to punch forward, you are going to supply an amount of force towards your bicep and tricep. Okay, yang mana yang contract, yang mana yang relax during front punching action? Which one contract, which one relax? Ni bukan soalan cepu emas lah. Just I need you to think about. Yang mana yang contract? Try to palpate your bicep and tricep at this action. During the forward motion, which one relax, which one start to tense up? Okay, yang mana satu? Mana satu relax, mana satu tense up? Front action, back action, front action, back action. So when you go front, yang mana yang lembut, yang mana yang keras? Bite and try, dua tu je. Jangan yang lain. Saya nak kamu tengok dua tu je. Okay, palpate. Put your left hand, okay, thumb at the bicep, the other fingers at the tricep, and do a punching action. You are going to notice that when you move forward, one part of the muscle is going to contract. Another part of the muscle is going to relax. And when you retract, you're going to notice that what the other part of the muscle is contracting and the partner relaxing. Okay, forward action. Yang mana yang contract? By ke try?
Bye, sir.
Huh?
Bye.
By, are you sure?
Yang relax kan, sir?
Bukan.
Forward.
Kita forward action. Kita forward action. Bicep dengan tricep, yang mana yang contract, yang mana yang relax? Yang mana yang keras? Belakang ke depan? Bicep, tricep. Humerus, radius, ulnar. Move forward. Bila kita move forward, yang mana yang lembut, yang mana yang keras? Berbanding dengan bila kita contract. Okay, macam ni, bila kita relax. So when you relax, like this, you retract your hand, you're going to notice that your bicep curl and hard. Depan, tarik belakang, cuba pegang bicep tu. Dia keras tak? Ke dia lembut? Okay, come on. Buat macam ni. Okay, can you see me? Ke enggak dapat? Okay, if you do like this, try to palpate your bicep. Keras tak? Is it hard?
Rasa.
Okay, when you go forward, is it still hard or it become relaxed? Go forward. Okay, still palpating your bicep. Now go forward. Retract. Go forward. When you go forward, is it hard compared to the previous one?
No.
No. Okay. Now palpate your tricep. When you move back, and then compare when you move forward. Okay, when you move back on retraction phase and then punch forward. Masa bila dia keras tricep? So masa kita relax, dia keras ke lembut? Compare tu dengan masa kita punch forward. Okay, punch forward. Always remember this one. When we retract, your bicep is going to be your agonist. Pasal dia yang akan contract in order to pull your hand back. At the same time, when bicep is your agonist, your tricep is going to be the antagonist. Bicep contract, tricep lengthen. Jadi dia akan lembut. However, when you punch forward, okay, when you move your hand forward, your tricep is going to be stretched. Dia akan keras. Okay, dia akan keras. And that one is the agonist. At the same time, your bicep is going to be your antagonist bila kita tegak. Okay, bila kita tegak. Jadinya, kalau masa ini bicep contract, masa ini bicep lengthening. Kalau dalam proses kita tumbuk, kita nak stop the punch, which muscles are we going to contract? Terbalikkan situasi tadi. Sini contract, sini retract bicep Jadi kalau kita nak berhenti separuh jalan, we go and we need to stop. Means we need to stop this amount of force. Ini force being delivered. Ini force being delivered. Where? At the bicep. Which direction? There, to you. So, if you try to have the action stop, means we need to have impulse, but not to you, is to me. Means we need to apply force in different direction. That is what happened when we try to stop. We try to purposely stop an action. Okay, jadi apa yang saya nak tunjuk kat kamu sekarang? If this leg swing at 8 radian per second in this direction, okay, forward, means that there are angular force being delivered there. Means that there are torque being given to the system, which cause the system to swing forward. Okay, now my question is, how much angular impulse needed in order to stop this swing? Means we are going to contract muscles and we are going to give a counter force in order to make 8 radian per second become 0 radian per second. So we know this will be omega 1, you're going to have omega 2. Tu cerita dia. How much force needed in order to stop this particular movement. Kalau dalam soalan dia tanya soalan betul dia, how much angular impulse must be supplied by the hamstring to bring a leg swinging 8 radian per second to stop. Berapa banyak yang hamstring kena bagi. Kalau tadi quadricep dah bagi satu amount of force, in order to make it swing, counter that action is by activating the another part of the muscle. So how much angular impulse needed in order to stop this particular movement? So dia dah bagi dah, dia ada omega 1, dia ada omega 2. So you can find out how much angular impulse by using the formula of change of momentum. Okay. So change of momentum. Jadi kita dah ada dekat sini angular impulse 1. M K square omega. Okay. Minus dengan M K square omega. Okay. So berapa kita dapat? Alright. So M, kita dah do have MK square? MK square is actually I, sama Jangan nak pergi cari lah. MK square ni I, dia dah bagi dah tadi. The leg moment of inertia is 0.7 kg. So we have 0.7 kg M square times with omega 2 kosong minus 0.7 kgm square omega 2 will be 8. So we have kosong minus 5.6 kgm square S. Jadi jawapan dia ialah negative 5.6 kgm square S. This is the amount of torque needed in the system. Kenapa negatif? Because yang lain tadi towards one direction, this torque need to be given in different direction. And it will cause the leg, the swinging leg to stop, to impulse. Okay, that is some examples of impulse. Okay, dapat? Amount of force being given. Kalau linear, again kita tengok balik konsep. If linear, when we give amount of force to the system, it cause the system to move forward. But since it is torque, meaning kalau kita ada satu system, we give force towards the system which will cause the system to rotate. Tu je beza dia. Linear impulse cause move forward. Angular impulse cause to rotate. That is the difference. The thing is similar. FT, yang ini pun FT. Tapi F dia bukanlah F, dia ialah torque. Okay. Ataupun FDT. Itu sahaja beza. We need to include the distance or the radius. Okay. If you recall back what we have learned, for both linear and angular kinetics, when we talk about angular, for kinetics pula. Linear, angular kinetics and kinematics. When we talk about angular and when we try to have relationship with linear, ini je penambahbaikan yang dia akan tambahkan. The inclusion of radius. So when you see an inclusion of radius, that is the case of angular. Okay, itu adalah angular impulse. Sekejap saya tengok satu contoh lagi. This one is angular momentum. Okay, velocity, the moment of inertia. Okay, yang ni dah sudah. Alright, we go to an example of momentum. Okay, let's see. Alright, so principle of angular momentum. H1 equals to H2 equals to H3. Okay, maksudnya mk square omega 1 mesti sama dengan mk square omega 2 mesti sama dengan mk square omega 3. Kalau ada 10 sampailah mk square omega 10. Kalau 12 sampailah 12. It will be similar. Okay, now is the case. We have a diver Okay, 50 kg diver. So kita tahu kg mass. Okay. In a full layout position. So this is a full layout, tegak. With a total body radius of gyration with respect to a transverse. Jadi kita akan ambil satu distance. So the radius of gyration for this fella is 0.45 meter. Dia pun jump or dive. Okay. She is jumping or diving. Right. And when he leave the springboard, okay, here, the angular velocity is 6 radian per second. Okay. The question is, what is the diver angular velocity here? Okay. Kita nak tahu angular velocity dia dekat sini. If the radius of gyration during tuck position. Okay. Ni kita panggil sebagai full layout. This is tucking. Okay. In tuck position, the radius of gyration reduced to 0.25 meter. So what is the new omega? So cuba cari berapa omega dia dekat sini. Okay. So these are the key. MK1 will always equals to MK2. Okay. Cari MK1 dulu. You are going to get how much omega during tucking. Silakan. Berapa jawapan dia? Okay, silakan kira. MK square omega equals to 50. K is 0.45 square. Omega is 6. This one is momentum. Gradient. Since H1 sama dengan H2, so H2 ialah 60.75 kgm square. This is what we mean as principle of angular momentum conservation. It will be equal. Now you know that will be the answer. Jadi kita bolehlah cari mk square omega yang kedua omega tucking. So equals to 50. K will be difference here. Omega 60.75. So 0.25 square times 50, we have 3.125. 60.75 equals to 3.175. 17 is 1212. 125 omega. So automatically the omega will be 60.75 over 3.125. 19.44 radian per second. Ini jawapan dia. So if you take a look here, during the full layout, the radius of gyration is longer compared to here. Okay, the radius of gyration layout longer than radius of gyration tucking. Since ini lagi besar radius of gyration, velocity will be lesser. So you know that when the radius of gyration reduce, the velocity is going to be larger. Jadi kita dapat jawapan yang betul lah. Velocity of rotation during layout is 6 and velocity of rotation during tucking is 19.44. Apa maksud dia? Maksudnya yang ini berpusing macam ni, lembab. Yang ini berpusing macam ni, laju dan banyak. Itu maksud the difference. Okay. So since dia laju dah banyak, the radius of gyration is lesser compared to layout phase. Okay, so that will be some of the example. Kita tengok lagi ada tak? Sekejap ya, sekejap ya. Okay. Okay. Kita tengok case. Sekejap ni dia bagi apa ni? Torque mk square omega. Alright. Okay, yang ini settle? Boleh? Kalau boleh saya akan proceed dengan contoh seterusnya tentang impulse. Are you okay with this one?
Okay, sir.
Okay. Alright. Now the derivation of impulse. So beforehand, we have learned about torque equals to change of momentum. We know that torque always equals to FDT. Okay. And we also know torque as mk square omega. Okay. So torque is momentum. Okay. Impulse is momentum. Alright. The other derivation of this equation is when they ask you about alpha. Okay, apa itu alpha? Alpha is angular acceleration. So if they ask you about alpha, if we take a look at this definition, change of momentum is acceleration. Okay, change of momentum is an acceleration. mv2 minus mv1. mv2 minus v1. Okay. This is actually linear momentum. So, if they ask you about change of acceleration, it is caused by angular impulse. And you can write it out as mk square alpha ataupun I alpha. Okay, I ni moment of inertia mk square. Ni derivation dia. Jadi sampai sini apa yang kita dah jumpa? We find this one. Torque equals to FDT. Torque equals to mk square omega 2 minus mk square omega 1 ataupun change of momentum. Okay, angular momentum. This is angular momentum. And now we have impulse. Angular impulse is also equals to mk square alpha. The simplified version of change of momentum. Ataupun it can be I alpha. Ni sampai sini. Ini hanya formula saja. Okay. Now, example. Okay, I give you an example. Alright, here they ask you about what is the resulting angular acceleration for arm and hand when the forearm flexor rotate to the elbow. Okay. Then kita ada jari. Okay. Humerus, radius ulna, phalanges. Okay, so soalan dia, what is the resulting angular acceleration? Tangan dengan jari. If this complex, okay, the mass of this complex is 1.7 kg. Okay, and then when the forearm flexor, so forearm flexor is a muscles here. Sorry, ni extensor, flexor. Okay, flexor. Flexor. Alright. If these muscles attach 3 centimeter from the center of rotation at the elbow, so we have the axis and the attachment, sorry, not like this. And the attachment, okay, the length here is 3 centimeter. Okay, 3 centimeter. Producing 10 Newton of tension. So means these muscles producing force of 10 Newton. Okay, given a 90-degree angle at the elbow and a forearm and hand radius of gyration. Okay, forearm and hand radius of gyration here. So the middle where all the weight being situated. Okay, this is dia punya radius 20 centimeter. Okay, alright. So the question is, when these muscles contract and it causes the hand to move, what is the acceleration if we apply 10 Newton of force? Okay, maksudnya sekarang kita ada 10 Newton of force, we apply to the flexor and it causes the hand to move. The question is, how fast the acceleration occurs? Berapa cepat? Jadi, case dia, kita nak tahu if we apply 10 Newton, berapa cepat dia boleh bergerak. If we apply 10 Newton, berapa cepat dia boleh bergerak. Okay, so that is the question. Okay, that will be the question. Okay, so this question have two parts. It has two parts. First, it has the parts of torque equals to I alpha. Ataupun we can have it as FD, torque equals to mk square alpha. This involving two parts. Okay, dia ni melibatkan dua bahagian. Kamu kena tengok betul-betul. Dia melibatkan dua bahagian. One bahagian is linear, another bahagian is angular. Okay, so I give you the question again. What is the resulting angular acceleration? So the thing that we try to find out is here, the angular part. What is the resulting angular acceleration of a 1.7 kilogram forearm, okay, forearm and hand when the forearm flexor attaching 3 centimeter from the axis? So the attachment point distance from the axis is 0.3 centimeter. 0.3 pula. 3 centimeter. So dia ialah 0.03 meter. Okay, 0.03 meter. Produce 10 Newton of force, 10 Newton of tension, given a 90-degree angle at the elbow and the forearm and hand radius of gyration of 20 centimeter. Okay, radius of gyration is 20 centimeter. We know that when we talk about radius of gyration, K. Okay, K ni bukanlah jarak daripada, contoh saya ambil kaki. Okay, ni dia punya thigh. Ini dia punya lower leg, dia punya feet. K is not the distance. Kalau saya kata berapa jarak thigh dia berputar, itu bukan K, itu ialah R. K is when we need to determine something like this. For tight, where's the middle of it? Middle to the radius of to the axis, ini K. Jadi dia bagi tahu dekat sini, forearm and hand radius of gyration is 20 cm. Means the middle of this complex. Inilah dia. Jadi kalau saya keluarkan tanpa muscles, okay, it will be, okay, we have flexor, hand flexor. Okay, flexor. We go for flex. Extend, sorry, flexor sini. Axis. This distance is 0.03 meter. The middle of the system to the axis of rotation is 20 cm ataupun 0.2 meter. This is K. Okay. This is apa ni? Ni dia punya D for top. Okay. So they try to find out mk squared. Jadi FD or torque is also equals to mk squared alpha. So F here is the amount of F in the system, which is 10. And D here is the amount of, is the distance between the force being applied by the muscles to the axis of rotation. Since it is parallel in line, okay, both is actually parallel with the axis. Jadi kita akan ambil terus jarak dia. M is the mass of the system, 1.7, and K square here is the radius of gyration to the system. Tadi D tu jarak force dengan axis. Okay, jarak force dengan axis. K is jarak gyration ataupun jarak titik tengah dengan axis of rotation, which is 20 cm, 0.2 square alpha. Kamu dah boleh dapatkan alpha. Okay, so dekat sini we have 0.3 equals to 0.2 square times 1.7. We have 0.068 alpha. So automatically alpha is 0.3 divided with 0.068. Empat point 4.41 radian per second square. Okay, meaning that if we apply 10 Newton, if the force being produced at the flexor is 10 Newton, it will cause the hand to accelerate. Okay, accelerate macam mana? Tangan kita kan bergerak dekat joint. So if our hand, this is our hand, this is the joint, it can only move like this. Ini pergerakan angular. So it will cause the hand to accelerate. Since the flexor activated, it will cause the hand to flex at a staggering speed of, or acceleration of, 4.41 radian per second square. Itu adalah kadar acceleration. So now what happen if we give, if we give the extensor, okay? Tadi flexor kan, sekarang katalah kita ambil extensor ni. Okay, the same thing. K equals to 20, M equals to 1.7 kg, and then we have D equals to 0.03. But now what happened if the extensor produce a force of 15 Newton? What is going to happen to the system? Is it going to contract? Is it going to be isotonic? Or is it going to be an extension? Means the hand is going to move downwards. Cuba selesaikan. Kita dah ada tadi. Okay. The first case, we know that the hand is going to move upwards at this rate. Okay, because we've been applied this amount of this amount of force by the flexor. Now what happen if the extensor yang bawah pula give 15 Newton of force? Okay, cuba selesaikan. Now we have two different amount of force being subjected to the system. So what will be the end of this system? Ke atas atau ke bawah? Silakan. Tips clue. We know that impulse is change of angular momentum, mk square omega 2 minus mk square omega 1. And we know that impulse is also mk square alpha. So if we change this equation, we are going to have mk square alpha 2 minus mk square alpha 1. So what is going to happen to the torque? Kamu akan dapat torque positif ke torque negatif? Silakan. You need to find alpha. Kita dah ada alpha 1. 4.41 rad per second square. Find out alpha 2. Okay, dapat. The end product is negative. Means that when we applied 15 Newton of force to the extensor, it will cause the hand to rotate downward. Tadi dia rotate ke atas kan, kita bagi that 15 Newton of force as the extensor, it will cause the hand to stop and actually rotating downwards. Ni counter impulse lah. Okay, so this is another examples of impulse.
Supposedly bukan 0.15
Mana?
ke?
Ni
Kan? 15 kan?
Sekejap. 0.2 kali 1.7 kali dengan 6.62. 0.45.
Yang
Kat
akhir tu, final answer tu.
This one.
Bukan 0.15.
0.15 ni kita dah tolak kat sini. So negatif 0.45 tolak 0.3. Ni negatif. Kan negatif. Tolak 0.45 tolak 0.3. Mana dapat? 1 pula kamu ni. Okay, 0.45 tolak dengan 0.3. Ini ke laut Cina Selatan ni. Sorry, nombor pertama saya salah. 0 tolak 0.45. So you have negative 0.45 and then you minus lagi dengan 0.3. 0.75 lah. Lain kalau kat sini positif. Kalau positif, yes, you are going to end up dengan negative 0.15.
Sorry.
Ni kan negatif dengan negatif. Negatif dengan negatif kita jadi tambah. Tapi ada negatif kat depan. This is the same case tau. Kenapa? Okay, kalau tak faham ni kan. Ataupun kalau tiba-tiba lah korang blank kan. Ingat benda ni. Ingat benda ni. Okay, Cartesian coordinate Maksud 0.45 is dia bergerak ke sini tau. Okay, boleh tangkap ni Okay, kalau kita ada 0.45 bergerak ke kiri, kita tambah lagi dengan 0.3 yang bergerak ke kiri. We actually add up all the length. Means it going to be double up the length. Ni maksud 0.45 tolak 0.3. Tapi kalau kata you tambah, macam ni tolak ni dia jadi tambah, what happen is, you have 0.45 ke sini, and then 0.3 ke sana. So result dia, katalah ni 3 cm, ni 3.5 cm. So 3 cm pada sini hilang. So you end up dengan hanya a portion, which is 0.5. Ingat balik yang dulu. Kalau kita ada nombor positif, tambah dengan nombor positif, dia akan jadi positif. Kalau kita ada nombor positif, tambah dengan nombor negatif, dia jadi apa? It depends. Okay, it depends. Kalau kita ada nombor negatif, tambah dengan nombor negatif, dia akan jadi negatif. Kalau kita ada negatif, tolak dengan negatif, tolak dengan tolak, dia jadi apa? Jadi apa? Dia akan jadi positif. Okay. Dekat sini, the first number is negative. Okay. And then kita tolak. Okay. Kita tolak dengan second number. Second number ni positif. Number dia. Maksudnya dia macam ni lah. Tolak dengan positif 0.3. Jadi sama dengan negatif 0.5. Tolak dengan tambah. Dia jadi tolak 0.3. Dapatlah negatif 0.75. Okay. Clear? Kenapa dia jadi tolak? Kenapa dia tolak? Dia bukan tambah, dia tolak. Dia section dia tolak. Kalau yang macam kawan kamu cakap tadi, kenapa bukan 1.5? Itu kalau dia tambah. If we add on here, and then dia akan jadi negatif 0.15 lah. Since kita tolak 0.45 tambah 0.3. But now 0.45 tolak 0.3. So dua-dua bergerak ke kiri. Okay. Those two is actually moving to the left. Tak ada yang moving to the right pun. Okay kah?
Okay je sir.
Okay, alright. We go to ini penambahan vektor Kalau kamu buka nota kinetics ada dekat depan sikit penambahan vektor, vektor composition. Okay, patella tendon. Okay, tibia, patella tendon tibia. Okay, so macam mana kita nak buat gambar dia ni? Macam ni lah kot. Tibia, fibula, femur. Okay, so we have patella tendon attached to the tibia. We have the patella here. At a 20-degree angle. So the attachment, the angle of attachment, theta dia equals to 20 degree. Okay, the attachment. And then it attached 3 centimeter from the axis of rotation. So the axis of rotation is the knee. The distance here is 0.03 meter ataupun 3 centimeter. Okay, if the tension in the tendon, okay, if the tension in the tendon, tension is force equals to 400 Newton, what is the resulting acceleration of the 4.2? Okay, so ni kaki bawah ni, this system mass dia 4.2 kg. Okay, what is the resulting acceleration if the radius of gyration, so from the axis to the center of the system, R pula, K, radius of gyration. The K is 25 centimeter ataupun 0.25 meter. So the question is, what is the radius of radius. What is the acceleration of the system? Means when the tendon, okay, when this tendon being subjected to 400 Newton, maksudnya there is force being subjected to the tendon, it caused the leg to actually rotate. Okay, so the question is, what is the acceleration of this rotation? Angular acceleration. So we go with the same equation, okay, which is Fd torque at the system cause acceleration to the system. Okay, sama macam tadi. Torque at this system cause an acceleration. Okay, so what is the amount of acceleration? Jadi kita ada force 400. Cuma dekat sini ada satu trick. This trick, please remember carefully this trick. If we compare this situation with the first situation here, okay, situation ini, the force being proposed to the system parallel to the axis. Okay, the force being proposed to the system parallel to the axis. Dia bagi tahu tadi 90 degree. However, for the second case, which is most of human case, the force being subjected to the system is in diagonal, means it has an angle. Okay, jadi ini case apa sebenarnya? Ini adalah case force begini. Force being subjected to the system at certain angle. Okay, when you see this kind of system, meaning that this is actually the case of some sort of projectile cases in terms of force being proposed. Jadi, FD ni, torque dia ni, dia bukan semata-mata 400 times 0.03. No, but we need to include the degree of penetration dekat sini. We need to include the degree of the force being applied. Macam mana kita nak include? Okay, when you see a case of human joint where the force being subjected at an angle, you need to include this. Include the angle. So how you want to include that? Okay, so force ni, okay, the force here is not F, but it is actually, you still remember this one? Kalau kita ada something like this, okay, where we try to find resultant, kita akan pakai apa? Sin ke, cos ke, tangent. Force, angle, okay, theta. Okay, so force here, when you see an angle, or most of human cases, this force is actually F sin theta. And then only D. Unless the angle of force being subjected is parallel, berselari. Tapi kalau angle dia tak parallel, not 90 degree, ada angle, you need to use F sin D in order to include the vertical part. Okay. So jadinya untuk soalan ini dia ialah 400 sin 20 and then only 0.03 equals to M. Berapa M dia? 4.2. And how about the K, the radius of gyration? 0.25 square alpha. Dapatlah kamu selesaikan soalan tersebut. Okay, apa kita dapat? Okay, we have sin 20. 20 trigonometry sin times 400 times 0.03. 4.10. Okay, 4.10 equals to 0.25 square times 4.2. 0.26 alpha. So alpha equals to 410 divide 0.26 divide 0.26, we have 15.77 radian per second square. Means that when we applied 400 Newton at the patella tendon, it caused the leg to rotate at an angular acceleration of 15.77 radian per second square. Ni kegunaan impulse lah. Means when we applied that kind of force, okay, towards the system, it caused the system to rotate. Itu angular impulse. Okay, that is angular impulse. Force that been given into the system, the force is in terms of torque, because when we talk about angular motion, it is rotation. Linear force does not cause rotation, but a torque causing rotation. So that rotation is angular momentum. That force is angular impulse ataupun torque. Dapatlah natang ni. Jadi kalau dalam most of human movement, we talk a lot in terms of angular kinetics and kinematics. Okay, when we talk about internal force. But when we talk about the derivation of force, the outcome of the force that is caused by linear force, that is caused by linear impulse, which we can actually observe in terms of linear momentum. Ni perkaitan lah antara kinematics and kinetics, both linear and angular. Okay, sampai sini. Okay. Boleh faham?
Boleh, saya boleh.
Right. And then let's go here. Just a bit more. Okay, ni dia bagi equivalency. Mass in linear is moment of inertia. Kadang-kadang kita lupa apa benda, tiba-tiba jumpa I is mk squared, sama. Okay, torque. Okay, force in linear is torque. Fd. Jadi kalau impulse Ft, torque, kalau linear impulse is Ft, angular impulse FDT. Senang je kalau lupa sangat lah. Okay, yang lain-lain sama macam dekat dalam nota tadi. Alright. And finally, we talk about mechanical behavior of body in contact. Collision. Collision cause impulse to be transferred. Okay, collision, pelanggaran. Okay, when we talk about collision, it is actually the change of force. Impulse. Okay, impulse. Impulse happen in collision. We deliver impulse during collision. Okay, during impact. Collision is impact. Alright. When we try to characterize impact, we can characterize impacts in two different nature. Okay, and it represented by coefficient apa ni? Coefficient of restitution ni, natang E ni. Okay, coefficient of restitution. To explain coefficient of restitution, there are two methods. One is by using this one. Okay, relative velocity after impact, relative velocity before impact. One is object one, two is object two. Ini kalau kita gunakan dua objek yang bergerak dan berlanggar. Okay, V is velocity after, U is velocity before. V is velocity after, U is velocity before. One is the first object, first ball. Two is the second object, second ball. So when it goes left and right, meeting in the front, this is before. And when it collide and move in a different direction or move in the same direction after impact, that is after. U ni nombor dua. Nombor dua. V. Okay. U is the velocity before collision. U1 object 1, U2 object 2. Collide, berlanggar. Kita ada dua benda, berlanggar. Okay. And bila dia berlanggar, maybe it goes different way, maybe it follows one another. And when that happen, that is velocity after ataupun V. Okay. Tu. Means here yang kamu kena faham, U and V, there are tendency of change in direction, the plus and the negative. Okay. That is one way. Another way, saya tengok mana dia buang another way ni. Another way ni lagi mudah sebenarnya, tapi kita guna bila case yang berbeza. Okay, wait for a moment. I'll try to find out it first. Kat sini saya rasa dia tak tulis satu je. Okay, dia bagi satu je. Sekejap saya carikan satu lagi. This second equation is being used when the case is actually involving height. Okay, height before, height after. Tinggi. Yang itu lebih dicari dia mesti tak jumpa. Tunggu tak cari nanti. Semua benda wujud. Collision not here. Sekejap ya. Kejap. Mana saya punya button ni? Okay, the second equation is coefficient of restitution. Okay, the second equation is this one. Okay, coefficient of restitution. E ni yang pertama tadi equals to V1 minus V2 over U1 minus U2. Where 1 and 2 is the object. U is initial value. V is final value. Okay, lagi satu equation dia, we can write this one as atau E square equals to HB minus HD. Okay, ataupun HB divide HD square root. Ni lah. Okay. yang mana okay, E is coefficient of restitution, H representing height, okay, B representing bounce, and D representing drop. Okay, contoh macam ni. Kita ada bola, okay, kita drop, this is HD, and then the ball bounce back, this is HB, the height in meter. Okay, so apa cerita dia ni? When we talk about collision, okay, it can be characterized by coefficient of restitution. And this coefficient of restitution is actually a numbers. Okay, it is actually numbers. That numbers is from 0 to 1, where 0 is perfect plastic and 1 is perfect elastic. Dia takkan ada lebih pada 1, takkan ada kurang pada 0. Dia akan duduk tengah-tengah. Okay, and most of the time when we calculate the coefficient, it will end up in between, nearing to 1 or nearing to 0, where if the numbers is nearing to 1, menghampiri 1, we know that it is near to elastic impact. Apa tu elastic? Elastic impact is a collision between two parties, between two surfaces, where after the collision, the amount of energy being restored and the shape of the object is retained. Ni, velocity of the system is conserved. Tapi kalau plastik, total loss. Okay, contoh elastic, we drop a soccer ball from level 4. When it hit the floor, it will bounce back, meaning it has kinetic energy being restored. And the shape of the ball will return to its original state. But what happens if we drop a watermelon from level 4? When it reaches the ground, it will absorb the force and it will shatter. A total change and total loss of energy. That is plastic. Jadi kalau kita buat experiment, when we collide things, when we drop things, and after the collision, both of the party retain the same shape. Bola dengan bola belanggar, dua-dua jadi bola. Cuba bola belanggar dengan steamroll. Tak adalah. Kereta dengan kereta belanggar. After that, you are not going to get a kereta lagi. It change shape. So that is plastic. Okay, that is plastic. Tapi kalau kata bola dengan bola, although kita sepak kuat mana pun, if it's still within the threshold, it will retain the same shape, it will retain the same amount of force. Tapi kalau kita sepak terlalu kuat, when it collide, it become shattered. Bola tadi berubah bentuk. It not round anymore. It will be flat. Itu bukan bola lagi. Itu plastic. That is the difference between plastic and elastic. And in order to test that, we are going to conduct coefficient of restitution calculation, and we are going to determine the numbers, how much coefficient. Okay, so saya bagi okay, this will be the end of our notes. I give you an example, just one example. Let's say we have a soccer ball. Kita ada satu bola sepak, and this ball we drop. Okay, we drop the ball from height of 2 meter, and after after the ball hit the ground, it bounced back to a height of 0.98. So what is the categories of collision occurs here? Jadi kita pun boleh gunakan yang tadi. A square equals to height bounce divided by height drop. So equals to 0.98 divided by 2. Apa kita dapat A square ni? 0.98 divided by 2, kita ada 0.49. So E equals to the square root of 0.49, 0.7. So is it nearing to 1 or is it nearing to 0? Yeah, dia dekat sini. Means that it is nearing to 1, which resulting this collision to be an elastic collision. Means that after the collision, the ball return to its shape and it retain the amount of energy within it. Okay, all kinetic and potential will be restored inside the system. Ini adalah contoh collision lah. Okay, collision and how we what can we determine by the collision itself. All right. So any question up until now? We have another 25 minutes. Ada soalan apa-apa?
So far, okay, sir.
Okay, so far okay. All right. So if you don't have any question, I have one announcement to be made. This week is week 9, and as we know, in week 9 we are going to have something. Let's see. What are the things mana kita punya scheme of works. Okay, week 9, that one. We are going to have quiz 2. Okay, and quiz 2 will be covering up until 2 topics, angular kinematics. And again, like quiz 1, it will be an objective quizzes involving only 10 questions. Okay, and I will be conducted this quiz as before during your tutorial classes. Okay, means that it will be conducted on what? Thursday from 3 to 5. So please answer the quiz according to your class hours and finish it up before the end of the quiz session. Means after 5, I'm not going to accept any more answer. Are you clear on that?
Yes, sir.
All right. So that's all for today. Thank you for your participation. If you have any question, you may ask. You may ask by writing in the Google Classroom stream, or you may ask me directly. Okay. Don't forget to take your attendance. And again, thank you. Assalamualaikum. We are going to meet again next week with the next topic of fluid mechanics. Okay, fluid mechanics and mechanics of biological materials. Right. Thank you. Assalamualaikum.
Waalaikumsalam, sir. Thank you, sir.
Yes,
Yes,
sir.
sir.
Waalaikumsalam.
Thank you,
Thank
sir.
you, sir.
Thank you.